duality theory, we'll look at a simple graphical illustration. In this simple case, we have the objective function f of x, and we have just one inequality constraint, g of x less than equal to 0. The Lagrangian is Lx lambda, which is fx plus lambda times gx, where lambda is a scalar and that's greater than equal to 0. The feasible region is the set of all points such that g of x is less than equal to 0. The primal theta p of x is the maximum of the Lagrangian with respect to the single scalar dual variable lambda, and theta p star is the minimum point of the function theta p. The dual theta d of lambda is minimization of fx plus lambda g of x with respect to x, and theta d star is the maximum of the dual function theta d. Graphically, we will show that in our simple case, the dual function theta d lambda is concave. And we'll see weak duality holding. The maximum of the dual is less than or equal to the minimum of the primal, that is, theta d star is less than equal to theta p star. We shall see that. And then we shall see that when f and g are convex and there is a strictly feasible point, then strong duality holds. Theta p star equals theta d star. These are the three things that we can see graphically. So this is the constraint optimization problem. Minimize f of x subject to g of x is less than equal to 0. This is an n-dimensional space, which is the domain of f and g, our two functions. And this plane is the fg plane, where the x-axis is the constraint and the y-axis is the objective. So if we take any point x in n dimensions, its image in this fg plane will be the point fx, gx. And this blue shaded region is the image of the entire domain of the vector x. And the only reason this blue shaded region is bounded is because I've just assumed that f and g are also bounded. Let's move this to the middle. So this region, the blue shaded region, is defined as f comma g such that there exists an x in n dimensions such that f is f of x and g is g of x. Now, noting that the feasibility constraint is g of x should be less than equal to 0, we mark off the infeasible and the feasible regions. This is g of x is less than 0, which is feasible, and this is g of x is greater than 0, which is infeasible. So everything to the right of this y-axis, the f-axis, is infeasible, which is shaded gray. Given any x, we can easily read off fx and gx. Likewise, this is fx and gx for some other x. We can easily locate the minimum of the function fx, and that's where this red dotted line, the horizontal line, is tangent to the blue shaded image in the feasible half plane. We have to ignore the infeasible half plane when we are locating the minimum, of course. Thus, we have found theta p star. Our next goal is to find theta d star. These straight lines in red are contours of f plus lambda g when lambda is fixed at a value of 2. The slopes of these straight line contours are negative lambda. The values of the constant are 3.5, 1, negative 1.5, and negative 4 for these 4 lines shown. These are the straight line contours of f plus lambda g when lambda is equal to 1. These are contours when lambda equals 0.5. Given any x whose image is fxgx, which is this red dot shown here, we can easily read off fx plus lambda gx by looking at where the straight line contour intersects the vertical axis. So this is the point of intersection, and this height is fx plus lambda gx. This contour corresponds to when lambda equals negative 0.5. However, note that lambda can never be negative, so this is disallowed. The straight line contours that we are allowed to draw will always have negative slopes. As we keep changing x, the image of x keeps moving in this blue region, and at some point we hit the minimum of f plus lambda g, and that's theta d corresponding to the fixed value of lambda. This is theta d when lambda is 0.5. That's the minimum of f plus lambda g. And how do we locate lambda d? That's where the straight line contour corresponding to lambda is 0.5 is tangent to this blue shaded image, and therefore this is theta d. The tangent where lambda is 2 and the value of theta d lambda, which is where the contour intersects the y-axis. The tangent when lambda is 1 and theta d lambda, where the straight line contour intersects the y-axis. This is theta d lambda, which we saw previously for lambda is 0.5. Observe that theta d keeps increasing as lambda is reduced from 2 to 0.5. This is theta d when lambda was 2, this is theta d when lambda was 1, and this is theta d when lambda was 0.5. The straight line contour is always pivots around this region of this blue shaded image. If we, for some value of lambda, which is 0.35 here, the maximum of theta d is reached. This is theta d star. The straight line contour is tangent at 2 places, here and here. What happens when lambda is lowered further? This is with lambda equals 0.15. The contour is now tangent to the blue region in the right half plane, which is infeasible. Thus, the x that minimizes the Lagrangian fx plus lambda gx for this value of lambda is infeasible. Also note that theta d begins to decrease now. It was here and now it's beginning to go down. Thus, this point is the maximum of theta d, which is theta d star. This is with lambda equals 0. It can be noticed that as we changed lambda, the value of theta d kept increasing until it peaked at theta d star and then it started decreasing. This illustration shows that theta d lambda is concave. Earlier, we had seen that theta p star is obtained by drawing a horizontal line at the minimum of f in the feasible site, which is this horizontal line here. Now we saw that theta d star is obtained by drawing a line that is tangent at 2 points, here and here. In our case, one was feasible and the other was infeasible. So this is theta d star and this is theta p star. And clearly theta d star can never exceed theta p star. It must be lower than theta p star. This illustrates weak duality. The difference between the two is the duality gap. Strong duality holds in this case where theta d star equals theta p star. Hence theta px and theta d lambda touch one another at the saddle point. This is a convex function. The objective is convex and the inequality constraint is also convex. Clearly strong duality holds. Theta p star equals theta d star. This is another case where theta p star equals theta d star. Now in this case, Slater's condition is not satisfied because this blue shaded image never crosses this vertical line. So there is no strictly feasible point. Therefore, Slater's condition is not satisfied here.